Welcome to Breadboarding. In the previous video, we managed to tidy up our 555 LED flasher circuit, and we also tried out this discrete transistor version of the 555 PCB, and that allowed us to test out a couple of the other points internal on the 555. And this is the oscilloscope trace that we got from the capacitor and from the output pin. This is video 6 of the how to use breadboards and retro digital electronics, and in this video we're going to start looking at the logic gates and chip families that we need to use with retro electronics. Probably worth first of all just looking at the difference between analog and digital electronics. So analog electronics really deals with continuously variable signals between limits. So if we look at some sort of alternating current like this, at any point in time, the exact value of this will not be a discrete value. And in fact, in this particular example down here is quite a good one. This actually shows a composite video signal that would go out to a monitor or a TV using the composite sort of connector. And you can see that there's different voltage regions within this particular signal that mean different things to do with all the various sync levels, brightness, and various other things like that. So that's analog. And digital, we're dealing generally only with two levels. So they're known really as true and false, on and off, 1 and 0, or 5 volts and 0 volts. Now, the reason why I've put ish there is, although theoretically most retro digital electronics does work off 5 volts, the actual signals we're dealing with are not necessarily 0 volts and 5 volts. They're actually somewhere in the middle. And we'll be looking at why that is during this video. So these diagrams come from SparkFun. Again, there's a good tutorial here. I've just tried to summarize that as briefly as possible. Now, before we start to go into the details of the logic gates themselves, we probably just need to have a brief look at transistors. Now, I've covered transistors, obviously, in summary when we've been looking at the 555 circuit over the last number of videos, but we've not really done anything specifically to do with transistors themselves. The first working devices were invented around 1947 at Bell Labs, and those guys there later got the Nobel Prize for Physics in 1956. Now, we use transistors in digital electronics, so they're really just used as digital switches. They are able to be used in all sorts of other modes of amplification and things like that. There is a lot of theory and background to do with transistors, all about the way how they're made and all the different N and P type layers and things. We don't really need to know much of that to get a working understanding of them for digital electronics. And if we actually look at this SparkFun tutorial, again, the SparkFun tutorial will take you through the different types of semiconductor, so the N type and P type, the symbols and pins. So generally we have two types, NPN and PNP. The NPN, it tends to be the one we use most of the time, and that has the arrow pointing outwards down towards this pin called the emitter. We have the collector, base, emitter, and generally with a PNP transistor, then it's kind of like the reverse way around. So we have the emitter, base, and collector. Not pointing in, I think, is the mnemonic they recommend for remembering which way the arrow goes. And probably one of the best analogies to think about with transistors is with water. And effectively what a transistor is able to do is, when it's on, it can just let the flow through. When it's off, it stops the water. And when it's in kind of an amplification mode, it can control linearly the amount of water coming through. So depending on the value that we set in the base of the transistor, we can actually limit the amount of flow going through here. But when we're using digital electronics, we're primarily only interested in this short circuit mode. And there are some more confusing terms used within the discussion of transistors. So it's in the saturated region of the transistor, and this chart basically shows differences between the voltage between the base and emitter pins and the voltage between the base and collector pins. But this is the sort of stuff that is useful to know, and I'm not saying that people shouldn't understand this, but you generally don't need to understand much of this to actually be able to use transistors in digital circuits. And then some of the diagrams I've got on the slide have actually come from here. So this one here shows a very simple on-off switch. So what we have here is an NPN transistor, so NPN, and PNP is the other type. So not pointing in is the NPN. And you'll see these called bipolar junction transistors. So the thing about being bipolar, this is kind of, I guess, the older technology. More modern transistors, certainly in modern chips, are CMOS, complementary metal oxide semiconductor. But we're going to be dealing with bipolar, and the TTL logic, or transistor logic, which most retro digital electronics uses, is using these bipolar junction transistors. And this circuit basically says that if we apply a voltage here, so in this particular case 5 volts, a current flows through resistor 1 down through to the collector to ground, and what that does is enables a larger current to actually flow through this resistor here, through the collector down to the emitter, and so the LED lights on. Now there's a key thing here is we need to include a resistor here, otherwise if a large current goes from here down to the emitter here, then you can blow the transistor up, a bit like you can do with the LED. So if we didn't have the resistor here for the LED, we could burn the LED out as well. So the symbols, the NPN has the not pointing in, and the PNP has the reverse arrow there. Now, quite often when the symbols are drawn, they're actually drawn with the collector at the top and the emitter at the bottom. However, the way how the PNP one is used most of the time is the reverse to that. So we'll look at that in a second. And this diagram is an animated one, actually, again, from later down in that SparkFun tutorial. And what it shows is that when we have a small current here, so about 4 milliamps is going from here down to here, and then it turns off. When it turns on again, that small current there then enables this larger current. So we've got actually down the bottom here 34 milliamps, which is basically the 30 milliamps from up here and the 4 milliamps from here. So the key things really are we need really about 0.7 volts across the base to actually turn the transistor on, and we do need a current limiting resistor here, otherwise we might blow the transistor up. Now this was the 555 diagram that we looked at in the earlier video, and if you remember, we've got both types of transistor here. We've got the PNP transistor, and in fact what I did here is this is the symbol that we just showed you previously, but in fact what we've done is reversed it, because if you see on the diagram here, in fact the way how the PNP transistor tends to be used is with the emitter actually connected to the 5 volt supply there. So in fact, quite often the way how the PNP device is used is with the emitter on the top and the collector on the bottom, whereas the NPN is normally done this way. But by convention, we tend to show the diagrams sort of this way round, but it can be a bit confusing. So I always found PNP transistors to be a little bit confusing. Fortunately, we don't generally have to worry about them too much within the scope of digital electronics. So before I launch into the different types of logic gates, I was just going to go through this other site. So this is probably the best site I've ever come across for understanding digital logic ICs, and it's a 4-part series, Nuts and Bolts magazine. So I'll include the link in the description below. I'm just going to quickly flick through a few bits here, and then we're going to go into some diagrams and go into a bit of detail about how these logic chips actually work. So you've probably got some awareness of logic chips. There's different types of logic gates, so AND gates, OR gates, NOT gates or inverting gates, and then we've got the inverted versions of those, so NAND gates and NOR gates, which we're going to come to in a few minutes. But covered the digital signals. This is a very simple inverter, so with one transistor we could make an inverter. So if you remember, we've got our input current limiting resistor here, and because we have this pull-up resistor here, then if the transistor's off, then we get the voltage coming through here to the output. So in fact, when that's 0, this is on. When the transistor's on, what it actually does is pulls this close to 0 volts here, and so when this is on, this is off. So it's a very simple inverter. Now, in fact, we're going to be going through and looking at the logic gates for the inverter during this video, and we'll see that obviously that this is a very simple case. And this one then has an additional transistor, which then makes it just a buffer. So in other words, the input signal and the output signal are the same. Now, it's possible to make logic gates out of other components. So for example, a simple OR gate where if either of A or B are 1, then we get a 1 coming out. So it is possible to do that with diodes. It's also possible to do this with diodes and a transistor. So in fact, this is actually a NOR gate. So we've got an OR from the diodes and then an inverted operation from the transistor. So this is a NOR gate. And then this is a NAND gate. So this is an AND followed by an inverted signal as well. It's possible to make these gates with diodes and transistors. It also introduces a concept of digital signals. So we tend to talk about the duty cycle, which is the difference between the mark and the space. So the mark is where it's high, the space is where it's low, and the duty cycle is like normally the percentage between these two. And also the concept of rise time and fall time. So a digital signal doesn't go from 0, say, to 5 volts instantaneously. It tends to take a little bit of time. And the rise and fall time is normally what we say for the time it takes to go from 10% to 90% of the peak voltage here. So you'll hear about rise time and fall times when you start to look into data sheets and things like that. And I know that can get a bit confusing. When we talk about digital electronics, we also talk about rising edges and trailing or falling edges. So when we start to look at some of the logic gates, they will sometimes get triggered or clocked on rising edges or falling edges. Now, if you have a positive pulse like that, then it starts with a rising edge and it obviously ends with the falling edge. But if you inverted that, then you would actually have the leading edge would be falling and the trailing edge would be rising. So in fact, if you want to switch a signal between rising and falling, then you can just invert it and then effectively you swap those two around. It also mentions a bit about debouncing things. So the 555 circuit we looked at in the previous videos, that can be used for, say, debouncing a physical switch. So sometimes when you press the button on a switch, the contacts will bounce for a very short period of time, but that bounce can cause problems with digital circuits. So this is where we get into the logic families. Now, in the early 1960s, after transistors had been invented, then the first logic ICs started to come out. The first technology really was resistor transistor logic, or RTL. And this is an example of a gate. So we've basically got a number of transistors just with these resistors. Then there became diode transistor logic, or DTL. But there were some problems with these in that they were limited to how fast they could run and also how much power they took. Another form of logic, which is used more on mainframe computers, and this is emitter-coupled logic. It's a little different in that it works a lot of negative voltages and things, and certainly the mainframe computers and Cray computers, supercomputers, used to use emitter-coupled logic. I'm not sure if they still do. So we're looking to try and get the optimal way of getting speed without actually using too much power. And in fact, what they came to was something called a totem pole digital switch. So a normal digital switch, we might have a pull-up resistor like this, and then we have a switch. So when the switch is on, then effectively it grounds the output down to 0 volts here. But when the switch is off, then the value will actually rise up to plus voltage there through that resistor. But because circuits quite often have some residual capacitance, so everything will have some level of capacitance, then there would be a delay taken for the signal to rise from 0 volts up to V plus because of the capacitance and because of this resistor. And that fundamentally limited the speed with which these switches could work at, whereas a totem pole relies on having an input here, and depending on the input, then either this switch or this switch is enabled, and that allowed things to be switched much faster. And in fact, we'll ignore CMOS for the moment. In fact, this diagram is something I'm now going to sort of jump out to. So this is really a basic TTL, transistor logic inverter, and you'll see that it requires more transistors. So rather than the one transistor we started at the beginning, we've actually got 4 here, but this actually had the right combination at this point in time of switching speed and power consumption. So let's jump back to the slides and we'll show this particular circuit and actually how it worked. So what I've done, I've copied the details, so this is the URL for where this has come from. So what we're going to look at, first of all, we've got the input here, we've got the output, and we're just going to be talking about ones and zeros here, so the exact voltage of here doesn't really matter, but what we've got here is an inverter. So what we expect is when we have an input of 0, we want an output of 1, when we have an input of 1, we want an output of 0. So this page we're going to be looking at the 0 with the output of 1. And so this text here from the article I've referenced there is actually what tells what's going on. But I've made annotations here. So if we put 0 here, what happens when this is 0 is in fact the current goes through this resistor, through the base, to the emitter, to 0. And so this will in fact turn on. So this transistor turns on. When this transistor is turned on, then this transistor here is connected down to ground through this transistor and the input of 0. And so this one will now be off. So when this transistor is off, then in fact what happens is the input to this transistor here is actually pulled to 5 volts through this resistor here. So this one comes on. When this transistor's on, then the output here is actually going to be connected to the 5 volts, but this one is going to be turned off. And so because this is turned off, this is the one that will pull the output down to 0 volts. So in fact, because this one's on, this one's off, totem pole output, we get a 1. And then the output here, as I said earlier, although this is running off 5 volts, we don't actually get a 1 or a true is not actually 5 volts. It's more likely to be closer to about 3.5 volts. And we'll come on to the voltage ranges which are valid for 1s and 0s a little bit later. So now we're going to look at the alternate case, which is when we have a 1 coming in and we expect to have a 0 coming out. So we'll just do the same thing here. So if we put a 1 coming in here, because this will be 5 volts and this will be close to 5 volts, then there won't be any current turning through here. So this is effectively disabled. That means that this will actually be connected to 5 volts through this resistor, so will be turned on. Because this is turned on, then in fact this one will be turned on. So we'll have a current coming through here, down through here, and so this will enable this one to be on. And because this one is now turned off, because of the path going through here, so because the input here is connected to ground through here, this one turns off. And so what we get now is 0 volts, but we won't get exactly 0 volts coming out here. It will be somewhere around sort of 0.4 volts or so. So again, we don't get exactly 0 volts, we only get 0.4 volts. So this is basic TTL inverter. Now TTL is the original logic series that came out in the sort of mid-60s. The later series that we're going to be looking at, the LS and the ALS, these had slightly different design, more sophisticated design, which allowed them to use lower power and to operate faster. But this is what we need to understand for how logic gates actually work at the low level. But from now on, we're pretty much going to be dealing more with the logic gates themselves. We might occasionally refer back to the data sheets where we get diagrams like this. So there's one other thing that we should also probably talk about. So we had this totem pole where we had 2 transistors on the output, but you'll sometimes also see that certain chips will be known as open collector or sometimes open drain, but the open collector, open drain basically means the same thing. And what this means basically is there are some times where we want the chip to be able to perhaps drive an external circuit, not necessarily at the 5 volt logic, but in fact we might want to be able to switch even up to 30 volts. And so with open collector, what effectively happens is we cut out this stage of the output. And so what this does is it only really when we have a 1 coming in here, then this transistor will be enabled and this will then be pulled down to close to 0 volts. And if we put a load on here, then this load could be connected to any other voltage up to 30 volts in some cases. So for example, if we were level shifting between a 9 volt circuit and a 5 volt circuit, then you could use this type of mechanism, and that you probably would have a pull-up resistor on this output would go perhaps to the 9 volts supply, for example. And in this particular diagram, the RX indicates external load, so it's not part of the chip itself. And this, so it was a little confusing when you look at this. So when you've got an open collector one, it basically means that you may need a pull-up resistor if you want to actually see a 1 voltage coming out. What it does mean is that we can connect it to different circuits, and this is also sometimes used where we want to have a signal, perhaps like a reset or an interrupt or something like that. We could actually have multiple outputs from multiple chips all connected together with a single pull-up resistor, and they wouldn't actually cause a problem. If we connected multiple outputs of this totem pole, then you would have a problem. So open collector is sometimes also used with microcomputer buses and things where we need to have a signal that perhaps that can be asserted by different components in the circuit. So you'll have them open collector with a pull-up resistor. So a lot of this stuff I'll be referencing Texas Instruments, and no particular reason other than that the Texas Instruments seems to be what most of the parts I buy these days from most of the suppliers. They do a logic guide which takes you through all the different logic series that are available. Now we're only going to be focusing on those ones which are used for retro digital electronics, but needless to say there's a lot of different logic series. So this diagram here I'm going to take you through in a second. This explains all the different logic series, and the original TTL one is in the middle there. And there's some other diagrams and things, and each of the different logic series has its own page in here with what its strengths and weaknesses are. So to go through all this sort of stuff and choose the right logic series you want to use, it would be quite confusing. But what I'm going to do here is to summarize it for you. So this is the Texas Instruments logic series diagram. So I include the URL for that document in the description below. And we look at the beginning here. The first TTL series was sometime around 1965-66. Generally became available to hobbyists in the early 70s. So the first electronics magazines with 7.4 series chips in for sale were in about 1970-71, I think. This needed to work off a pretty precise voltage, really as close to 5 volts as possible, although it does allow a bit of tolerance. But it could actually work up to 35 megahertz. Now, I did briefly mention the CMOS, and CMOS came out a little bit later than that, the late 60s, early 70s. There's the CD4000 series, which is similar to this 7400 series, but it was specifically for CMOS. Now, CMOS was a lot lower power and could work off 3 to 18 volts, but it was a bit slower. So at that time, it was only about 8 megahertz. So we're not going to be looking at the CMOS side of things for the moment, although everything modern is pretty much everything is CMOS these days. But when we're talking about our legacy microprocessors, so the Z80s, 8080s, 6502s, 6800, 6809s, 8088s, all those sorts of things, these are all going to be using this type of logic. Then around the mid-70s, the LS series came out. My understanding was perhaps a little faster, but it was mainly it was lower power. So it actually reduced the power requirement for this, and also had a greater ability to drive other inputs. So its fan-out was able to drive twice as many other chips than the original TTL series could. Then sometime around the mid-80s, the advanced LS versions came out. Now these were capable of going faster and lower power, and again had better fan-out capability, so the ability to drive more chips connected to its outputs. We've talked about the 4000 CMOS series, and the only other one really would be the HCT. So these are CMOS, but the HCT chips are actually TTL compatible. So the voltages that they use for the ones and zeros, the trues and falses, are actually compatible with the TTL ones. Whereas if you're using the HC ones, then those voltage levels are different and incompatible with the TTL one. So you need to be careful. If you are buying modern chips, you need to get HCT ones, but I would recommend really sticking with LS for the moment. So this is really the logic series and my recommendation. So the 7400 series, the original transistor logic, 1966. I think the earliest magazines I saw in the UK was about 1970, where you could buy these chips from mail order. Then the low power Schottky, as they were known, so normally known as LS for low power Schottky, introduced in 1976, again for hobbyist use there, may have been available a little bit earlier. Then the advanced low power Schottky was introduced in 1985, and one of the projects I'm looking at the moment is the compact Despro 386, to a 386 breadboard PC, and this in 1986 started to use ALS chips as well in some places. The advantage of this one is that it had a higher fan out. So this had a fan out of 10, I think this was 20, and I think this one, if it was talking to similar chips, could maybe do up to about 40 in some cases. Whereas this CMOS HCT series, which is TTL compatible, it is a bit slower and it can't drive as many TTL chips from its output. So it has a fan out of 10, so it's closer to the fan out capabilities of this one. So for retro microcomputer projects, I recommend using LS and ALS series. LS is still widely available, and most of the chips are available in the DIP form. So this is like the dual inline package, so the form we can plug into breadboards. The only one I have found that isn't available today in DIP form was the 74LS646, which is a buffer latch chip that I've used in a couple of projects. So you can only really buy this in DIP form off eBay. You can buy it in other flat pack profiles, but you just can't get it in DIP form. ALS tend to be used for buffers and latches, in particular in the video controllers where things need to work a bit faster. So these are certainly rated up to about 40 megahertz for a lot of the parts that are more complex, which is capable of being used in video controllers. Some of these parts may start to struggle above 25 megahertz. But the only issue there is you can't get all the ICs in DIP form. So in retro digital electronics, 5 volts rules. So all the microprocessors and integrated circuits from the 70s and 80s that I've talked about already run off 5 volt power supplies. Those 5 volt power supplies need to be pretty accurately regulated, probably between about 4.75 and 5.25 volts. And these are compatible with a transistor logic 7400 series. The CMOS complementary metal oxide semiconductor 4000 series, and some of them the later chip series from the 80s onwards, can run off power supplies from about 3 volts up to 15 or 18 volts depending on the series. And a lot of breadboard tutorials will use 9 volt batteries with the CMOS chips. So just be aware, whatever you do, do not use 9 volt batteries with any of these TTL chips or microprocessors, as you will kill them. Obviously, some of the more modern chips, so some of the microcontrollers and things, may be a bit more flexible, but just be aware that you need to be using 5 volt supplies like the USB power supplies or a bench power supply. But most modern digital electronics, so Raspberry Pis, Arduinos, Atmegas, run at 3.3 volts and use CMOS. Some of them do have 5 volt parts, so I know you can get 5 volt Arduinos which are compatible with 5 volts. And some of them also run off 5 volt USB power supplies, but then the signals are generally 3.3 volts. And also be aware that the modern microprocessors and RAM tend to run off even lower voltages, so 1.1 or even 1.2 volts. So the modern chips on modern motherboards work off a much, much lower voltage to reduce the power dissipation. So this is a diagram that's come out of that Logic Families document from Texas Instruments, and just really to summarising about the voltage levels. So you generally can't damage a 5 volt chip with 3.3 volt outputs. So 3.3 volt going to 5 volts, okay. But if you feed outputs from 5 volt parts, will damage 3.3 volt inputs. So if you send 5 volts to 3 volts without some sort of level shifter in the middle, then you may very well damage the part. TTL and CMOS parts can't reliably work together without consideration for these different high-end voltage levels, and this is what we're going to look at in a second. So you do need sort of either level shifters, which are chips that will actually reliably translate the TTL and CMOS logic levels and voltages, and you can also use pull-up resistors when you're using TTL to CMOS. So we'll cover that sort of later in the series, but this series we're just going to be looking at 5 volts and TTL using the LS and ALS chips. That's the document that we've got this from. Now when we're looking at this thing here, I'll zoom into it, but what you'll see is that these symbols that you'll have in a lot of data sheets and things can be a bit confusing if you don't know what they mean. The VOL means the output low voltage, so this is what a chip will send out for a low signal on its output. The output high voltage. Then on the input side, the input low voltage, so this would be the highest input voltage that the chip will understand as being low. And then the input high voltage will be the lowest voltage that the chip will understand as being high. And then these threshold voltages come in later when we talk about Schmidt triggers. So what you'll see here is with TTL, we've got a 5-volt supply, but in fact, the output low voltage, let's just zoom in here, might make it easier. So we've got the voltage output low of 0.4 volts, but we'll understand inputs up to 0.8 volts as being low. The intermediate zone here, where things are undefined, and we'll look at that in a few minutes. And then we've got the output high voltage, which should be a minimum of 2.4 volts, but the input high voltage, as long as it's over 2 volts, then we'll recognize it as being high. So again, as you see that when I put on the slide a few slides ago, 5 volts-ish and 0 volts-ish, then that there is the ish, and this is almost like 3 volts below the 5-volt power supply. And the problem comes when you try and connect things to CMOS, is that CMOS has different levels. So the outputs will tend to be, and the low level will be similar, but what it treats as an input low is quite a bit higher, so you can see the difference there. When we come to the high levels, then in fact the output high is generally 4.5 volts and the input high is 3.5 volts. So you can see here, if we were trying to drive a CMOS input from a TTL output is only guaranteed to give us 2.4 volts, and in fact CMOS needs 3.5 volts to recognize as a high voltage. So understanding this diagram is the key thing to understand when you're dealing with TTL. You're dealing with 0.8 and 2 volts really for the inputs, and 2.4 volts and 0.4 volts for the outputs, whereas for CMOS you're dealing with higher voltages. Now the advantage for CMOS is that it is more resistant to interference, but in combining the two logic chips it causes you problems. Logic gates generally are defined by the inputs we tend to know as A and B, so A and B, A and B, A and B, obviously we only have A there, and the output Y. And these are the symbols that are commonly used, and the first one here is an AND gate. So basically in order to get a true output or one output, then you need to have a 1 and a 1. So you see here, this is known as a truth table. So the only time we get a 1 coming out of this is when both of the inputs are 1. Whereas the OR gate, as it might imply, means that if either of these is 1, we get a 1 here. So you can see here, the only time we get a 0 for this is when A and B are 0. Exclusive OR is a bit of a strange one, but it basically only produces a 1 when the two inputs are different. So if you have 2 zeros, we get a 0, 2 1s, we get a 0, but if there's a difference between the inputs, then we get a 1 coming out of there. And then the buffer is what we'd seen earlier, that a buffer basically just takes the input signal, boosts it and sends it out as it was. So quite often we might use buffer chips to interface between a microprocessor and the rest of the computer so that it boosts up the signals and doesn't damage the microprocessor. Now these ones down the bottom are pretty much the same as these, apart from the output is inverted. So this little circle on the end normally means that the output is inverted, and sometimes you'll see symbols where there'll also be a circle on the input, and that means that generally that the input will be active low. Now the NOT gate is a thing that we've actually looked at already, and what this is just an inverter. So if you put a 0 in, or you get a 1 out, and a 1 in, you get a 0 out. So effectively you could take these three here, combine it with an inverter, which as we saw may be as simple as adding 1 or 2 transistors, or 1 or 3 transistors to the output, and it would actually make one of these. So this is basically this with an inverter on the end of it. So you'll see that the NAND gate, or negative AND gate, will only produce 0 when both of the inputs are 1, and the NOR gate, negative OR gate, only produces a 1 when both the inputs are 0. Then the exclusive NOR, then if A and B are the same, then we get a 1, and when they're different we get a 0. What I'm going to break the video now, so we're up to about half an hour. So what we've managed to do is introduction to chip families and a bit of background on logic gates. In the next video we're going to be looking in more detail at the NOT logic gate, the inverter, a little bit more background to the chip families to talk about some more topics like fan in, fan out, and some of the differences in timing for the different chip families. So the next video we'll be covering the inverter in more detail and doing some experiments with breadboards to see what happens with different voltage levels. Then we'll be going on to look at the AND, OR, XOR and buffer gates in video 8. And then on video 9 we'll go on and look at the NAND, NOR and XNOR. If you don't want to miss out on future videos, then please hit subscribe. And if you found the content interesting, please hit like, it just helps to make it available to more people. Thanks for watching.